All right, good morning, everyone. This is yet another exciting episode of Oracle to Cassandra Core Concepts. So this is part 2 in the series, and we are going to dig into some data model today. It's me, Patrick McFadden. I'm Chief Evangelist for Apache Cassandra, and who do I have with me?
With data stacks?
All right, you cut out a little bit. Say that again.
Sorry. Rachel Bedreski. I am also an evangelist with data stacks.
And now you know how to use your microphone, right?
I do.
All right, good. All right, yeah, you're a professional.
What the mute button is and is not.
Yeah, well, you use it effectively. So we're going to just launch right into this. So what did we do? So last episode was about the transition from Oracle to Cassandra, and it was more of a conceptual problem that we're dealing with. How does it work? We highlight some of the differences, and it's just to ease you into this concept. So if you're coming from an Oracle background, again, in case you didn't hear this, I've been an Oracle DBA forever, since the 1990s, and then that happened to me. I know, that happened to me. I had to make this transition at one point, and so this is near and dear to my heart. But that happened last episode. I want to say last week, but whenever you're watching this, the last episode was about that transition. And again, just to try to ease you into it. Today, we're going to be talking about the Cassandra data model. Straight up, this is going to be gory details, and so much more of a technical discussion this week by far. I'd say this is probably one of the meatier of the three, and we'll be digging right into the Cassandra query language, which is CQL. It's top down going to be beef. Where's the beef? It's going to be part 2. And the next episode is going to be about building an application. We'll preview it a bit more at the end of this talk, but it's really going to be about top-down. How do we build an application? So now you have all these concepts. Let's do this. Let's build this an application. So Rachel, why don't you start us off?
Yeah. Well, last week we ended it like, well, where's the catch? You know, everything about Cassandra seemed, pretty cool, right? It's designed for the new world of applications, multi-data center replication, always on. I mean, it kind of seemed like a rainbow farting unicorn. It can do everything. Well, I mean, we did talk about the fact that it was for transactional purposes. It's not particularly good for ad hoc style queries, But just to remind everybody, and for those who did not make last week's and did not click on the Watch Now link, typically what happens is you have an application that is attached to a Cassandra ring. And the Cassandra, that application is attached through some sort of driver. And as the application inserts data into the Cassandra ring, the primary key is hashed and it's given a token. And then each one of the nodes in the ring has a token range that it's assigned, and the data is inserted properly. You can choose to have a replication factor. In this case, we're doing a replication factor of 3, meaning that each piece of data will live on 3 nodes on the ring. So it was pretty straightforward, but this is how we got the replication to work in Cassandra. Go ahead.
Oh, sorry.
That was good. No, perfect timing.
All right.
There's got to be a better way of doing this.
There should be. Hey, WebEx people, I know you're on the phone. Fix it so we can have 2 people controlling slides. Okay, so what's the first big concept we're going to cover today in CQL?
Well, we're going to talk about a static table. So let's start with something that everybody's very familiar with. This is a create table statement. It should look vaguely familiar to those who are even completely uninitiated to the world of Cassandra. You have things like a table name, column names, column types.
Now, it's an interesting little segue here. So what's interesting, I feel, about this is what's missing, right? If I came from Oracle and I have done quite a few of these in my day, varchar, what's the missing part there?
So this looks like the pseudocode I used to write, like I used to jot down on napkins, right? Because it would be like I didn't put some of these details in, but now you don't even need it. It looks like it's missing some
size
values, yeah.
Yeah, so I think that's the first thing you should notice is that, for instance, with a varchar text, any of the types that CQL uses do not have a sizing assignment. So you don't have to say a varchar 255, which is something that easily can be done, right? I could just do that in my sleep. But that's really because of the way that Cassandra works. It's sparse data. So the data that you store is the data that you have on disk, whereas with Oracle, when you create a database and you create a data file, it will allocate that space and the blocks and everything before you even write data to it. And that's not the case with Cassandra, obviously.
Well, no, and because Oracle came from a different world. It came from a world of mainframes and where size, was very, very important as far as, allocation. And this is a NoSQL database, right? This is a little bit more free form. We don't have these constraints anymore, and we don't need the constraints anymore. More importantly.
Yes. And a lot of people ask, like, what's the limit? Well, on a varchar, you're looking at any of these types, actually, the size is 2 gigabytes. So I like to call that a practical limit. Don't ever try to write 2 gigabytes into a column. I think your application will barf before you finish writing it. So it's a big number, and it is doable. I've seen people try. But that's very interesting, right? So that means that every type that's in Cassandra has a pretty huge limit. And yeah.
So the question is why would you even have types to begin with? But the types, a type in the create table statement actually tells Cassandra to make sure the data that's being put there is actually an integer or text or varchar. So it does actually have a reason to live, and its reason is to make sure that the data type is correct when you insert data.
Oh yeah, so that's a huge thing. Is a lot of folks think that NoSQL means no schema or it's just whatever you throw in the database. Cassandra is very strongly typed schema, and you're right, that enforces the types. So if you put in int and try to put in some string of some sort, it will throw a violation. It'll say no, you can't do that. So this is how we can map out our application logic to a table using types, and you'll see that we have some exotic types in here too, not too exotic, but maps and sets, and we'll get into that in a bit. So moving on this table.
Right, we have a primary key designation. Yay, again, something we're very comfortable with. The primary key designation on a static table in Cassandra does exactly like it does in Oracle. It will make sure that piece of data is unique. It's uniqueness thing. But, we like to be multitaskers here, right? It's not just for uniqueness. It also becomes our partition key. So whatever that first value of the primary key designation is, it's what is going to get hashed, if you remember back to that previous slide, and tells where that data lives in the ring. And that hash value is going to be between, we'll talk about it in a little bit. But yeah,
you're getting ahead of me here. Yeah.
Sorry.
Yeah, so let's get to the concepts here. First concept, row.
Right.
Let's look new.
Ooh, look, it's a row. It has a partition key or a primary key and a couple of columns. That seems pretty standard. A partition is going to be multiple primary keys with multiple different types of columns. And this is
but it has the same partition key.
But it has the same partition key, exactly. And we're going to see later about how this actually represents how the data lives on disk. So just for definition, we've got rows, and then we've also got partitions. A table is a collection of partition keys. So we've got partition key 1 that spans multiple logical rows, and partition key 2, which spans multiple logical rows.
And?
Next. So then we have the concept of a keyspace, which is a collection of tables. And you may think of this also as a schema or a database. It is pretty much exactly the same thing. So the concept of tables and key spaces are probably very familiar to you if you lived in a relational database world. Tables is a collection of rows, and a key space or a schema is a collection of tables.
So let's talk about how this works. Here's your first shot at the DDL and Cassandra query language CQL. This is just an insert statement, and it should look really familiar at this point. If you came from Oracle, I don't know if there's a whole lot of difference, maybe other than just some syntax, very small syntax issues like single tick versus double tick. But this is an insert. So we have a table called videos, and this video table is going to store, we have this a data model online, and we'll be talking a lot about it next week especially, but there's a data model online called Killer Video. And this actually exists as a web application. You can look at that online. We will provide that in the show notes later, the link to this. But this videos table is an entity of, it's just a video, and a video has users, etc. And this is an insert statement for that. And what I want to look at is how does this work when I write insert statement? How does it work in Cassandra? So when we have a table name, we have some fields, and then we have our partition key. Now the partition key is required when we do an insert, just like you would have a primary key that's required on an insert with Oracle, because you need to.
Partition key, Patrick. Can you just explain what that is?
Yeah, that is an odd number. If you are familiar with a UUID or a GUID, that's exactly what that is. And we use this quite a bit in Cassandra. When we get into more of like an application design, we can talk about when to use it, but what I can tell you is this is a really good way to create ID numbers with Cassandra, especially any distributed system, mainly because what you're getting here is a guaranteed unique number in the universe. At least that's the plan.
Is the UUID unique to Cassandra, or is it a concept that we borrowed from someplace else? Everybody
uses it. Like I said, GUID. So if you're in Microsoft land, it's GUID. They call it a globally unique, not universal. I like that. They got burned on that 640K thing, so they're pulling back a little bit. So the GUID, UUID is in, I think, about every driver I can think of, or every language, Java, Python, Rust, you name it. They all have a UUID, a way to create a UUID. And there's different types of UUIDs, but in this case, it's a type 1 UUID. So the partition key is required. We're going to throw in some values. I want to talk about the partition key, though. Let's dig into that right now. So we have a couple of inserts here. Now, I've created a much smaller version of that. We didn't have to get too big. So I have two inserts here. Now, if you'll notice, I have the first two partition keys. Yeah, it may take a minute to parse that, but those are different. And those two inserts, what will happen with those? Now, you mentioned this before about the hashing. Let's look at that specifics. So when I pass a partition key to Cassandra, what it does with that is it does a hash with that. And we use Murmur 3 now. We have used MD5 in the past, and that may be still what you're using today. But this is a consistent hashing algorithm. And consistent hashing algorithms have the guarantee that if you have the same input, you'll always get the same output. So if I hash these UUIDs, I will always get a number out, and that is assigned to another 120-bit number, which we call a token. Notice where this might come in, right? So tokens, again, are that consistent hash, that 120-bit number. This is going to show its position in the Cassandra ring. This is how, because Murmur 3 is a random partitioner, it will randomly partition this value across your ring, and so how you have it spread out around many, if you have 1,000 nodes, you'll get 1/1000th, and then if you have 2 nodes, you're going to have 1/2. This token value is assigned always to that value of the partition key. So this is how we can always get it back, and this is how we always know where it'll go, and it will be evenly distributed throughout the system, which is great. No.
Sorry.
Oh, sorry. There. You were going to say?
I don't remember now.
Oh, sorry. I ruined it. Okay, sorry. I'm sure it was epic. Anyway. So what about the next kind of table? How about that? I'll make it up to you. Talk about this one.
Type of table? What do you mean the next type of table? These are the only tables that exist in databases, right?
Yeah,
wrong.
Exactly.
Right? No. So this is a NoSQL database. So that static table that we just described to you is where relational databases end, right? There it is. It has a number of columns and a primary key, and it's stored on disk as rows, and that's it, because that is what could be done. We now have a new concept, and this concept is a dynamic table. And the only difference in this particular table, if you notice, it still's got all the, got UUIDs and timestamps and texts and no sizes. But look at the primary key designation. It has 2 values, which again is very typical in a relational database world. But in the Cassandra world, that second value has special meaning. And what the special meaning of that second value is what's called a clustering column. And that is what, so video ID is actually metadata. Video ID is never, the word video ID is not actually stored in the table. What's actually stored as the column name is the actual video ID, so a UUID. That is the new column name, the actual video ID. That. Yeah, let's talk about this, because this is definitely jumping down the rabbit hole, right? We have completely left the realm of traditional data modeling, and we're in someplace else.
Yeah, this is very specific to Cassandra, and something that, you and I talk to users all the time, and I think this is probably the concept that has to get over the fastest, because it will make or break your data model. So pay attention, class. This will be on the test. The primary key relationship, how does this work? And so if we look at the primary key that we took from the last table, we have a tag and we have a video ID. So we know that the tag is a partition key. We know that the video ID is clustering column. This is just terminology, right? We're talking about how, if you and I are talking about, this is what we designate these as. But what do they actually mean? So we know that the partition key, being data model, that would be one of the tags. We know that that's hash, right? So we're going to use that. And in this clustering column, we have now, with a partition key, clustering column will put these things into a logical row by themselves. So this partition will, physical row by themselves. So the partition key says, hey, all this data is co-located. So everything that has to do with data model, all the video IDs associated with that word data model, I want to physically be next to each other on the disk. I want to cluster those together on the disk, hence the word clustering column. And there is an order to this, and in this case, the order is not as easy to figure out, and I do have a better example in a minute here, but it's the UIDs. And if you'll notice, each one of this, so for data model, we have 3 videos that are associated with data model. This is a one-to-many relationship. And
it's obviously sorted to me. I mean, duh. That's...
Yeah. I do 120-bit sorting all the time, and I'd say that's correct. Yeah, not really. When we look at something that's a little more humanized, like an integer or a string, it will make a little more sense. But this is what we mean by clustering. It's actually clustering these values together on the physical disk. So back to the select. You want to talk about how a select works?
It works just like a select works.
I know. That's what I love about CQL. It has few surprises other than when you get into the data model itself of Cassandra, but it is still very familiar. And I hear some people, you do too, I think, Rachel, when we hear people say, well, you guys are trying to reinvent SQL. No, I don't think so. I think why reinvent something that works pretty well? I mean,
yeah, I just think of it as we're just expanding some of the definitions of it, but otherwise it looks exactly the same. And
from a programming standpoint, it makes a lot of sense, because give me some data from the database. As a programmer, this is a syntax that works really well. Now, I know there are alternatives, but this works pretty well. So with a table name, fields. Yeah.
Oh, wait a second.
That partition
key is required? What? That's new. What's up with that?
Well, yeah, I'm glad you asked that, because this goes into what the partition key actually means, right? What is it? What does the partition key do? So whenever I select this data, now what if I just said, give me name, description, added date from videos, period, and I just grabbed all the things? Well, that's a different problem. What if you have 1,000 nodes of data and there's 1 trillion records? What are you going to do with that?
Well, even if you have a less amount of data, I mean, what would your application do with all that and pushing in millions of rows through the wire, right? I mean, let's remember, this is for transactional workloads, right?
Right. So we as a as programmers, need more control over where the data is, and that's about data locality. And that's what the partition key is going to give us with that hash. But we also have some control as well with the order that we put the data on disk. So what we're trying to build here is a high-performance data model, right? And I mean, I feel like that's always been the case. Remember, if you remember last week, we talked about that was the problem we're trying to solve, is the database is slow, right?
And you know what's really slow? Sorting.
Yes, it's very slow. Yes. So here's a more complicated example, and so this is another example that I use quite a bit, and this is killer weather. We have a lot of killers out there, and this is storing time series data, and raw weather data is just a table that does that. There's a weather station ID, and then I've broken down the month, year, or the year, month, day, and hour, broken those down into individual parts, and then just storing a temperature. So if you look at the inserts here.
Why do you have parentheses around that the partition key?
Good question. Now, what I can, yes, you're good for questions. The primary key is, if you notice, has a lot more going on than just one partition key, one clustering column. Now, I put the parentheses or the brackets, if you're in Europe, around WSID because I wanted to make sure that you know that this is a partition key. This is being very correct with my syntax. Now, if I wanted to add more columns into those parentheses, I could group together columns into one partition key. Let's say I wanted my weather station ID and my year as one partition. This is a design decision. Again, something we'll talk about in the next episode, but this is what that means. Now, when you have multiple partition or multiple clustering columns, it creates a new thing for us. It gives us some control. If you look at the inserts here, Rachel, look at this. It's inserting data, and the only thing that's really changing is the 7, 8, 9, and 10. Those are the hours. So every hour, this weather station is giving up its temperature. Okay, and that seems like something I'd want to keep in order or retrieve in order, right?
Well, yeah, it would be nice. I mean, or especially clustered on disk, all the Julys together.
Right. So this is what it would look like, right? Now, let me go back one and look at that last statement here, the clustering order by. This is when you start leveling up on your usage of Cassandra. And one feature that I feel is going to make your data model sing, and this is a performance issue. This is on insert, I want to control the order that the data is sorted on disk. So if you look, the natural or sort order for integer is ascending. I've overridden that. I've made the integers now all descending. So basically what I've created is a reverse data model, right?
Oh, I see. And that way the newest data is going to be at the top all the time, because it's probably the data that I access the most often, rather than the newest data being at the bottom.
Right. So if you look at the table format that I have here, this is the table of that data that I just inserted. The hour 10, the one that was just inserted, is now at the top. It's the closest thing to me.
Do you have to break it down like that? I mean, could you just have an entire timestamp as your clustering column?
You could, but the reason I break it down into that is because the order is important, and the order that you use the clustering column. So if I do a select, I can do a select off the partition key and then the year, or I can do a select off the partition key, the year, and the month, or the year, month, and day. But because of that order, I can't do the partition key and the day. You have to do them all in order from left to right. And it gives me some granularity because I know it's all in a single partition of data, meaning it's all clustered together. If I ask for all of 2005's data, I know that I'm doing a single read off of the disk. It's clustered together on the disk.
So basically we're saying that you always have to have the partition key in your where clause, but your clustering columns are optional, but they go from left to right. If you have, right. If you want the one furthest on the right, you actually have to use the ones on the left first. Right.
And correct, I should say. And yeah, be careful when you say that. So correct, you would do that as a matter of order that you set them in the primary key. And speaking of order, what we've just created is your favorite function.
Oh, my data's sorted. How nice.
You've created the order by initially and efficiently in the beginning. So you get the order by descending. This is how you do it. And it's a very, very powerful data model.
It is a very powerful data model.
It's probably powering a lot of things that you're using today in a mobile app or a web app. And because I think I've spread this one around plenty enough. So let's talk about the right path from last week and how this looks.
Well, but I mean, because here's the question, right? I said earlier that sorting is expensive, and I've spent, before I came to DataStax, I was 15 years of data warehousing experience, and a lot of time was spent sorting data, and a lot of time was trying to push your order bys into memory and all that stuff in order to actually make it performant. The amount of twisting and turning that I had to do. So. If we say that we're doing this for speed, speed of retrieval, yeah, but where do we pay for that speed of retrieval? And here's where I think it's really cool about the way that Cassandra amortizes the cost of a write over time. So we have the client, and it's inserting data. We recognize our insert statement. It finds the node, so it hashes that partition key. It determines which node it needs to go to. And then it writes it writes it first to the commit log, and that commit log is a sequential file, and it just keeps writing it. And when a new file needs to happen, a new file comes up. It's not, there's nothing really managed except for just sequential writes. The second place it writes is to memory, and it's going to put in the partition key and all of our clustering keys and our actual values, which in this case is the temp, into memory. Memory is very fast to retrieve from, so if somebody's reading from memory, it just comes out pretty quick. But eventually memory,
Hold on. Now it acknowledges. Got to say that.
Yeah.
You're done.
Well, just back to the client, yes.
That's why it's super fast.
Good write. Okay, yeah.
I think that's important, right? Because this is why Cassandra is really, really fast, because it writes to a commit log, writes to memory, and then you're done.
Yeah. Okay. Yeah, you're right. Sorry.
All right. Moving on.
But eventually memory fills up. We're not to the point yet where we have unlimited memory on our machines. It'll be great when that day comes, but for now, RAM is limited. So eventually data has to go to disk. And this is where the sorting happens. So this smaller amount of data that lives in your memory is actually sorted at the time that it's flushed to disk. And it's flushed to something called an SS table. The SS table stands for sorted strings. Aha! So we've now sorted the data by the clustering order by.
I think you've cut out on me.
What? Hello? Am I not here? Can you hear me?
All right. I don't hear you anymore, so I'm just going to assume that you're not there. Maybe I'm here.
Can you hear me now?
So anyway, we're flushing out SS tables. When we have SS tables going to disk, we're going to have multiple SS tables getting written out, right? And those multiple SS tables are, oh, I can't hear you anymore, Rachel, sorry. Can you hear me?
Yeah, I can hear you.
Okay. Was I just talking to myself?
I don't know. I could hear you before. Can you hear me now?
Yeah. Must be the. I'm gonna blame cats and pipes or something.
Yeah, this is the whole pipe full of tubes or something. All right. Yeah. Anyway, as I was saying, the data is sorted into these sorted strings tables, and it's sorted by that clustering order by statement that we saw earlier. So these SS tables are immutable, and they are written every time that the mem tables flush. But eventually, there's a number of SS tables that build up, so a process comes through called compaction, which will merge various sort of strings tables together, put the data correctly in the right order, and create a new SS table. That's called compaction. And compaction is something that you do need to be aware of, because it probably will run all the time in a well-tuned system. And it's something you do want to tune for. Again, you're amortizing the cost of your writes over time, and this compaction is a cost. And it's a cost particularly in CPU and in I/O.
So I get asked this question a lot, Rachel. It's like, what happens if I have an outer order write? What happens? The compaction process is what covers that. If you have that weather station, let's say that it's kicking out weather data, and it goes offline for a period of time, or you get some error and it misses a few hours, and then later comes online and reestablishes its connection, that out of order data will be recombined during the compaction process.
Yeah, it's not an issue at all. And and the compaction also gets rid of data that's been deleted, because we'll be talking about deletes later on. But deletes happen in two phases. First, data that is going to be deleted is tombstoned, and then after a matter of time, compaction will remove those tombstones from disk and give you back disk space.
Right. So here we are back to the storage model. Now we'll just wrap this concept up. So we're back to selecting some data from the disk, and just to reinforce what we've talked about before, when I do a select from the database and I give it a particular partition key, this weather station ID, but then I give it the clustering columns, I give it a year, month, day, and year, month, and day. If you see this, like what you see here is this data that's sitting on the disk, or that's sitting in front of you, like this rows and columns. That's what programmers want to see, right? Well, this is actually how it's sorted on disk, and this is really what you need to understand about partition key and the ordering. Now that I do an order, I do a clustering order by and reverse it. Now, whenever I insert new data, it's actually going to the beginning of that record, and that means that as new data is appearing, it's now becoming the first record there, which makes it a lot because it's merged and it's sorted and it's stored sequentially. So now, when we get back to the read path, this is where we actually get the payoff, right?
Yeah, exactly. Because all right, so we now have our select statement, and notice that we have all of our partition key is there as required, and because we want to go down all the way down to the hour, and we're doing a range scan on the hour, that we also include the year, month, and day. We could include just the year and the month, the year, month, and day, or the year, month, day, and hour. So the client sends out the select. It, again, chooses the node that's appropriate based on that partition key. And then the SS tables will retrieve back the data sorted back to the client for retrieval. Well,
in the mem table, and yeah, and then back to the client, yeah. So then, and that's a really, I think that's important, is that a lot of people say, well, ask me the question, hey, if it inserts in the mem table, does it just read from the mem table? Sort of, but it needs to go to disk. This is a persistent system. It has to go to the disk to get that data. And there's no two ways about that, really. There is an option in DataStax Enterprise for an in-memory database, which it does not do that. It just stays in the mem table. But Cassandra standard uses it has to go to the disk every time, no matter what.
It's good to point out that in-memory compaction strategy for all in-memory data can be done on just a slight amount of data, right? You don't have to say all your data will live in memory. You can just choose hot data live in memory, and then warmer data that goes to disk.
Right, exactly. So you mix and match, and that's, yeah, exactly. And it is a persistent system. It has to go to disk. There's not an in-memory database at all. So this is what, let's go back to our disk again. So this is how we stored it on disk. Now this is why it will be fast, because when we ask for the data, we're going to ask for the partition key. The partition key goes to a single node, no matter how many we have in the universe. And you could have the small cluster, big cluster, doesn't matter. It's still going to go to a particular node for that because of the partition key. And we're going to do that single seek on disk, because disk seeks are the worst part of your system. Do not forget, disk seeks are measured in milliseconds, microseconds if you're lucky and you have a really fast like flash storage or maybe even SSD, but that will be the slowest part of your operation. So doing one seek, awesome. And when it does that single seek, it reads it all in one sequence, reads it all into your table, your CQL table. You get sorted by event time, rows and columns. Everyone is happy, and programmers love it, right?
Well, why do programmers love it?
Well, because programmatically working with rows is a lot easier. When you ask for a set of data, you can iterate over rows, grab the columns. It is just an easy way to work with data. Rows and columns are a preferred format. Now, there may be better ways to do it, but I'll tell you, this has always worked well for me, and I like it.
I think it also is not, you don't have to change a whole lot about the way your application works if you want to convert to a NoSQL system.
Now, going back to our first discussion, we've always tabulated data as humans, and creating tabular data is not a bad plan, right? Because we seem to like it. We've done it for thousands of years. No, for something completely different, but not today, right?
No, I mean, we can't just have a NoSQL database without some surprises and some changes, right? Some cool stuff.
Yeah. So these are really the Cassandra specifics, but they will help quite a bit. And this is where we move on from the traditional Oracle style data model, where we have some really cool features. And some of these are some that I use all the time in my data models. You saw it already. Let's start out with collections. So here's a very simple one. It's just a set. Now, a set of tags, that means that we're denormalizing our data here. And when we get into application design, we'll talk more about that strategy. But by denormalizing, we're grouping our data together and we're making it faster. And this is because of how Cassandra works. We have a partition key in all our data. Well, a set allows us to have a very dynamic part of that data model inside of a dynamic table. So a set of tags would be like the data model Cassandra. Like, think about tags like on YouTube or something. And this is a set that has a column name and then the CQL type inside the greater than, less than. That is for ordering. So whenever I create a set, because the set is ordered by the type, it's going to be collated by the UTF-8 or like a string ordering.
And also make sure you're putting the right type of data in there too, right?
Also critical, yep. So if I did a set of timestamps, it would order it by time. If I did it by integers, it would be ordered by ints. A list is very similar as a column name and a CQL type, but the CQL type in a list is not used for ordering because the list is the order you put it in. So the order you put it in is the order you get it out. Not my favorite collection. It's a little heavier. It requires more overhead because it has to sort every time you do an insert. I stick with set as much as possible in these cases. List is one that I'm not so hot on, but it's there, and sometimes list is important. And if I wanted to change my my CQL type, or if I wanted to make my set a list, I'm sorry, I put a set in there, didn't I? Duh, bad slide. So if I had my list of tags instead of my set of tags, then I would be saying that the order is somehow important, which it isn't really. So my last one here is my map, and this is probably one of my more favorite data types of all. I'm not even in CQL, but it's very dynamic because you get a key and you get a value. And so it creates a nice, I don't want to say it because someone's going to hold me to this, but it's like a database inside of a database, right? It's a key value database inside of your table. But here's the warning. Do not go nuts with this thing. The most you can put in there is 65,000 for a reason, because there's a lot of serialization costs that you're going to start incurring. And it's really meant for small, dynamic, key value type sets. And if you need more than 65,000, this is when you and I have that discussion of how to better do data modeling it with the table instead of trying to use a fancy collection to make it fit.
So how does it end up that these things get stored on disk?
Well, it's interesting because what we're doing here is smoke and mirrors in a way, because it's still being stored as a clustering column in a way down on the disk. And so all of these values are being clustered together in the same partition. And that's pretty critical, right? We know that if we put a partition key and then we have them all clustered together on the disk, that you will get a faster data model. Well, we do the collections abstract that for the user and then put those together on disk as well.
And it also allows you to manipulate items within the sets, lists, and map through CQL very simply.
Yeah, and it's just and because most programming languages have set, list, and map as a standard collection, it interfaces really nicely with your application. So let me move on. Whoop, back. So here's your favorite.
Aggregates, yes, the analytics side of me loves aggregates, and these are actually fairly new. to Cassandra, so this might be a shock to some of you out there who've been.
I'm sure.
Not
yeah, I bet you there's people out there saying, "I didn't know you could do this." Yes, you can.
Yes, you can. There's 4 currently built-in aggregates, so there's not all of them. They're not all of the things yet. We've got 4. We're very happy about 4. They just came out recently, but they are built in, and they you need to use it with the partition key. That it doesn't take away the requirement to not have a partition key in your query. They act just like you would any of these other aggregates. I'm not going to go into the details of how of what a max does, but I want to point out down at the bottom here in our CQL shell is there's something missing. And it bothers me because I write aggregates with group bys and halvings, and that is typically how you would write a
like an SQL aggregation. Yeah, you have to. You can't do an aggregation in SQL without doing a group by or something.
I mean, this is the way that I always wanted to write them, but I always got that nice little syntactical warning. You need to group by. Okay, fine. So what's different here? How do these aggregates work differently that they don't require a group by?
Well, that is the partition key. Now, so what we've known already, right, is that partition keys create their own grouping of data. And that's how you gather data together and using the clustering column for ordering. But you get a group by and order by using a partition key and clustering column. So this is why the warning here, if you look at the example here, I'm grabbing that raw weather data table. I have an example here where I'm doing the min, max, and average temperature for one weather station, so one partition key, over a particular year and a month, which totally handy. But notice what I've done there is I use one partition key and 2 clustering columns.
Interesting, because it's already grouped, right? The data's already grouped.
It is. So that is the fine print. Don't do this without a partition key, because what you're going to be winding up doing is a full cluster scan. And
we don't like doing full cluster scans.
No, full table scans, we try to avoid those because they sucked. Now we're going to do a full cluster scan. Those suck even more.
Right.
So let's not do that. And that opens up the whole conversation of using something like Apache Spark with Cassandra, which is definitely built to do full cluster scan, but way out of scope for this discussion. So
beneath those aggregates, so they're not normal aggregates, are they?
No, they're not. They're actually just built-in user-defined functions. So this is another thing that's now in Cassandra 2.2 and is not quite the trigger that you expect. And I say that because if you're used to using PL/SQL, or you're doing just any kind of trigger work in any other language or any other database, you know that there's a lot of things you can get internal introspection on. You can do things inside the database. User-defined functions are built in as a pure function. So you have a function that takes a CQL type, and it's usually a part of a column, and that pure function doesn't rely on any outside data at all. That's why it's pure. So the input parameters are manipulated by something pure inside of Java. You can also use JavaScript. You can use Ruby. You can use Python. And that function will somehow manipulate that data. And the functions can then you can use those to create aggregations. And that means, hey, do aggregations over a certain range of data that I provide, like a partition. And then you can create your own user-defined functions. Now, like I said, max, min, average, those are all included. Count, those are all included because those are kind of the easy button. I've seen some pretty interesting things already with these. I'm kind of excited to see what users come up with for a user-defined function. But this is definitely an interesting and useful change to Cassandra.
Cool.
There you go. The final coup de grace. What about? But I like ACID. I like transactions. Rachel, help me.
Well, you don't. I think we talked about dropping ACID last week, didn't we?
Don't do that. Not on the Golden Gate. Something about that.
So if Cassandra's is not an ACID compliant database. Specifically, the consistency portion of that is a little bit different, and actually we're going to talk more about that next week on how consistency works in Cassandra. But that doesn't stop us from requiring sometimes a need for a little bit of locking. Just a little bit goes a long way. Not every single transaction requires a heavy lock, but there are some transactions that do. And for example, race conditions. So when you are in a distributed system and you've got somebody signing up with the same username in different parts of the world, there needs to be a way to make sure that those don't end up colliding with each other, because the way that Cassandra works is the last right wins, and that's not very good for application consistency. So there is a concept called lightweight transactions with Cassandra, and they're fairly easy to implement. I mean, you get a pretty big hammer with just a couple of words. So right there it says if not exists, you add that into your insert statement, and that's pretty much it. That will actually initiate the process internally to make sure that this data is going to be written, and it's not going to be overwritten by another transaction coming very quickly after it.
Yeah, and this has been something, well, those of you that are new to Cassandra, congratulations, you missed a very bad period of time where people were using things like Zookeeper to try to maintain this consistency. And
or like recipes and Asiatics and stuff, right?
Well, any way you could possibly do it to mimic this, but because this is built into Cassandra, we are looking at Paxos under the covers, and that's a pretty established consensus protocol. So, and it lives inside the cluster, and I think that's the key. Things that happen outside of the cluster are independent. Bad things can happen, and you don't know it, and you get a really inconsistent state of your data, and dogs and cats living together, total chaos. So, so what else can we do with this?
Well, I was going to say I wanted to make the statement also that this is a read before a write, and it's a few round trips. So use it judiciously because it will affect your performance, no doubt about it.
Yeah, it's not the cheap option, but I will save you. And so, like anything else with Cassandra, and I've heard this many times before, is understand the internals. Well, this is an internal you should understand, is that there is round trip, and so it will take longer. But just don't use it for all the things.
Yeah, tell us about this. This if not exists on the table. What's up with that?
Well, this is really just another one of those, hey, I need to make sure that I'm the only one doing this, or it doesn't exist type thing, and it requires a locking to make sure that it works. And so the create table if not exists is really there so that instead of saying create table and then it does come back with an error of some sort, exception of some sort, is that it'll just do a no-op. So when you run that, it'll say just do a no-op, don't throw an error. Again, it uses Paxos to make sure that all this is happening exclusively. So it's an easy thing to use. So what about updates, though? This is a standard update, and there's some danger here because an update can overwrite data. And how is that true? Because there's no constraints. That is not something that's built into Cassandra. And a constraint violation wouldn't happen if this data existed. What's it going to do, Rachel?
It will go ahead and write it. It's going to go, okay, cool. Let's delete the existing one. So where that particular ID equaled that value.
Yeah, exactly. It's like my 7-year-old on a skateboard. Just don't get in its way because it'll mow you down. Yeah, bad. So in that case, I mean, but these are perfectly fine. In the case where you know that you have something that's somewhat idempotent, or you're working on a progressive data model, updates are rarely used, I think, in Cassandra. It's interesting. I see more data models with inserts than anything. Updates are not as common. But let's put a little lightweight transaction on here. So I'm trying to update this with a primary key, okay, what if I want to make sure that I'm being very exclusive about that operation? Well, we can do that too. So this if right here at the end, if you'll notice, is a conditional. It's a conditional update. And what I'm saying here in this conditional update is, hey, update the videos and give it this name, but only if this if it's from this user ID, and this user ID equals this user ID. So I've created a condition where I'm going to make sure I'm not overwriting someone else's video. Now this is a very simple example. You can think of some other things, but you can use any field inside the partition. So it could be user ID, it could be added date, whatever. This is pretty powerful. This makes update a very powerful mechanism when used with Lightroom transactions. So deleting data. Let's face it. I think we made this point last week, is that we don't really like deleting data, so I don't even know why we're covering this. We should.
You have to delete data eventually.
So how do you do that?
Look, you say delete from. And again, you give it a partition key, and it will actually wipe out that entire partition. It's pretty cool. You know, there's also the availability to truncate tables. Yeah. That's probably a better way of deleting data. Mm-hmm.
Absolutely. Yeah, and this will. So what's interesting about a delete, though, is it's a write. It writes tombstones. And
yeah, I talked about that a little earlier, didn't I? I jumped ahead of the game.
That's okay. That's all right. It's all valid. Tombstones are a marker in the system. We won't go into, if you want to learn more about tombstones, there are much better, longer discussions about tombstones. The thing you need to know about it is that it is marking in your database that that data is no longer valid. It doesn't actually physically delete it off of the disk.
Right. At the time you make the delete, and that gives you the ability to go back if you've made a mistake.
Yeah, and well, and it's not even that careful. It's more of a distributed systems problem. Because if you have data spread out all over the place, you have to make sure that everyone's on board with that delete, right?
Everybody cool? Everybody cool with this delete? We haven't tried to do something else to here. And there's things like zombies and stuff. I mean, it's a great topic, really. We should.
It is, yeah. No, the big fear is
on the zombie apocalypse. That would be fun. We should do that.
Tombstones. I think it would be pretty cool. Yeah, and it's what I think that's the biggest fear, is that your data returning, like somebody saying, "Yeah, I got that data. You missed that. Oh no." So here's my favorite feature of all time, and I say that because I use it all the time. So order by, it's like my second. My favorite is TTLs. And why? So what we're looking at here is a way to, the time to live, the TTL. And the expiring data, especially in time series data or in a very transient data model where you have data coming and going, I've seen some crazy use cases with this. And essentially what you're doing is you're marking your data whenever you insert it. You say expire that data after 30 days. And the way I explain a TTL is this is a free delete. It's actually less than free. And the reason I say it's less than free, if you've ever done a delete on Oracle, what do? If you have a lot of data to delete, you're going to have to either turn off your redo logs or watch everyone suffer badly because it puts enormous load on your system as it's chewing through all your data. Well, expiring
all your indexes, etc.
Oh yeah, it's just there was like a whole routine. Like, I'm going to delete data. Okay, let me turn off all this stuff, right? Oh, and then we'll do it at night because God knows what it'll do to our users. The beauty of the TTL is that once that data is expired, it just disappears. And it doesn't. What I mean when it disappears is the users no longer get to see it, and that it will eventually just not get copied as compactions happen. That's why it's less than the delete. It just doesn't move data anymore. So it's very, very, very low down the process lane. And it will not create a whole lot of problems. Good for you. I've seen some crazy stuff on this. I had one user that was processing 250 terabytes a month and expiring it after 30 days. So he had like a 30-day ring buffer of 250 terabytes. It's pretty cool. All right.
Wait a second. Wait. Before you do that, before we go there.
What? What'd I do?
Is this another UUID? What is this TTL? That doesn't say 30 days.
Oh, that's a very important point. I'm glad you're here. That's in seconds. So the TTL is in seconds. Yes. And that,
because I work with Cassandra, I know the number of seconds in 30 days memorized. That's sad.
Fun fact, you can say how many seconds are in 30 days as a Google search, and it will tell you. So yeah, it's 2.5 million seconds in 30 days. And so spend each one of them wisely, because that's how long your data will last.
And at least spend a good 3,600 of them joining us next week, because we're going to talk about joins, because there's not been any, if you haven't noticed that, we haven't done any tables here in our CQL that are joined together. And that is because there are no joins.
Yep.
So next week we're going to talk about why isn't there any joins, and what do you do about that? And then how do you design your application, both from the logical side and the organizational side to the physical side. Like, how do you actually take these concepts that we've been telling you about the last 2 weeks and make your application work with Cassandra?
Yeah, this is a top-down discussion. I hope that we can wrap everything up and make you a little more successful in your next application with Cassandra, because you've learned a lot about the parts, the bits, the pieces, and let's just put them together. Our intent here is to make you really good at doing this, so that everyone thinks you're an ultimate badass. We want that. We want you to be the badass. Show everyone how cool you are by this really cool app you built that doesn't seem to go down ever.
That's our job.
That's our job. And we would love to see you. Love to see you at the Cassandra Summit. And so we'll be there live September 22nd through the 24th. We are going to do training with O'Reilly. O'Reilly's going to do certification for certified developer, Cassandra developer, which is really cool. That'll be the first one ever. There's tons of talks, 130 tracks, lots of big companies, small companies, interesting people talking about interesting things. Just be there. It's free. Or if you want to get priority, here's a priority pass. Use Rachel's. Somebody used mine once. And there's a priority pass for getting 25% off certification. So we hope to see you there. All right, we have a couple minutes left. And Devin, I know you're on the line out there somewhere. Can you maybe pass us a couple of questions here? And just keep in mind, if you type a question into the chat, we will answer those in a blog post after the fact. So you will not be forgotten. You will get covered, but just today we're going to cover just as much as we have until the top of the app. So Devin, got anybody?
Oh, yeah. So here's a question from Tracy. In your first SQL, you did not have the same number as values as keys. Can you explain this? Typo, or is metadata populated by Cassandra?
The same. Oh boy, that's a tough question. I didn't.
It could possibly be a typo.
And it could be, but I think actually what you're asking is there wasn't the same number of columns that I inserted in. You can have sparse amounts of columns. The most important thing is you have to include the partition key and the clustering columns when you insert data. So those have to be there.
But it's actually very common to have a data model for certain types of tables that we'll go into a little bit more next week, where you just have the partition key and a clustering column, and you actually don't have a value. The actual cell can be null, but the column name or the clustering column needs to be populated.
Yeah. And if we didn't get that right, tell us we're totally off base. Tell us why, and we'll answer it in a blog post. Devin, you got another one?
If delete does not remove data, how does that impact the performance of a sorted table?
And you're right, that it does actually impact performance. And there are tracing tools in Cassandra that will tell you how many tombstones are you reading over if you're finding that your read performance is suffering. If there is a tunable out there that allows you to say how soon do you want data to be removed from disk. I think by default 10 days. But it will eventually get removed from disk. And if you are finding that you're reading over a lot of tombstones and it's affecting your read performance, then you might want to fiddle a bit with that setting.
Yeah, that's a really important one. So we're at the top of the hour. I'm sorry we only got 2 questions in. Again, we will answer your questions. And these are, that last question was obviously a thinker. You're paying attention. Good class. And we will be back next week for our final installation of this Oracle to Cassandra business. And we'll be talking applications. So hopefully you'll be there. Thank you very much.
Thanks for joining.